On November 14th, 2023, a spacecraft launched 46 years earlier, built with computers less powerful than a modern key fob, traveling through the darkness of interstellar space 24 billion kilometers from Earth, started talking nonsense. Not an interruption in its signal, not a weakening of its transmission. Voyager 1 was still alive. It was still pointing its antenna at Earth. The carrier wave was still arriving at the Deep Space Network dishes in Goldstone, California and Canberra, Australia, right on schedule, a faint whisper of radio energy crossing more than 22 light hours of empty space. But the data inside that signal, the actual science and engineering readings that Voyager had been faithfully packaging and transmitting every day for 46 years, had been replaced by a repeating pattern of ones and zeros that meant absolutely nothing. NASA described it as the call still being connected, but Voyager's voice replaced by a monotonous dial tone. The most distant human-made object ever created, an ambassador of humanity carrying a golden record with greetings from Earth's nations and the sounds of ocean waves and Bach, was sending home gibberish, and fixing it would require a team of engineers to remotely reprogram a 1970s computer from 24 billion kilometers away using documentation that was half a century old, calling retired engineers back from their homes because some of the people who had built the system had died, and nobody else fully understood the code. It would take 5 months. And when it worked, when Voyager came back online on April 20th, 2024, returning readable data for the first time since November, what it sent back was the story of everything it had found in the most unexplored environment in the history of human exploration. And some of what it found, the scientists who analyzed the data said plainly, should not have been possible. To understand why what Voyager 1 has been discovering matters so deeply, you need to understand where it is and what it crossed to get there. Voyager 1 was launched on September 5th, 1977, 17 days after its twin Voyager 2, from Cape Canaveral, Florida. Its intended mission was a 5-year journey to Jupiter and Saturn. Both giants were visited successfully. Voyager 1 returned the first close-up images of Jupiter's Great Red Spot in detail, discovered active volcanoes on Io, photographed the 4 large Galilean moons in detail never previously possible, and then swung past Saturn, returning extraordinary images of the ring system and its moons before using Saturn's gravity to slingshot itself upward out of the plane of the solar system. That gravity assist in 1980 put Voyager 1 on a trajectory heading away from the solar system faster than any other object humanity had ever launched. From that moment, it was on a one-way journey into the unknown with no possibility of return and no plan to stop. It carried 12 scientific instruments. It carried 3.6 watts of usable power from its plutonium thermoelectric generators, barely enough to power 2 Christmas tree bulbs. And it carried a 12-watt radio transmitter whose signal, crossing 24 billion kilometers of space, arrives at Earth so faint that the receivers must detect it at a power level 20 billion times weaker than the electrical current in a digital watch battery. For 35 years after launch, Voyager 1 traveled through what scientists call the heliosphere, the enormous bubble of charged particles, magnetic field, and solar wind that the sun blows outward in all directions, creating a protective cocoon around our solar system that extends roughly 3 times the distance to Pluto. Inside the heliosphere, the sun's influence defines the environment. The solar wind, a constant outflow of plasma from the sun's corona, fills the heliosphere with particles traveling at hundreds of kilometers per second, and the sun's magnetic field threads through it, creating the physical boundary that separates our solar system from interstellar space. On August 25th, 2012, Voyager 1 crossed that boundary, the Heliopause, and became the first human-made object to enter interstellar space. Scientists confirmed the crossing in 2013 after analyzing data from Voyager's plasma wave subsystem, which detected an abrupt increase in the density of electrons surrounding the spacecraft, consistent with the much denser interstellar plasma compared to the near vacuum inside the heliosphere. The confirmation made international headlines. Humanity had officially reached beyond the sun's domain. But the crossing itself was not what the models had predicted. And what Voyager found at the Heliopause, the wall it crossed, the condition of the environment on either side, was the first of the discoveries that scientists describe as something impossible in the context of what they had expected. The models of the Heliopause developed over the preceding decades had described a boundary that would be relatively thin, relatively calm, a smooth transition zone where solar wind pressure balanced the pressure of the interstellar medium and the two environments gradually merged. What Voyager actually measured was something completely different. As it approached and crossed the Heliopause, Voyager 1's instruments registered sudden, dramatic shifts in particle density and magnetic field strength, not a gradual gradient, but an abrupt, sharp threshold, almost as if the spacecraft had passed through an actual wall rather than a diffuse boundary. The magnetic field inside the heliosphere measured by Voyager's magnetometer for years as it approached the boundary, was expected to bend and deflect significantly as it met the interstellar field. Instead, Voyager found something that the NASA Jet Propulsion Laboratory described as a surprising result. The magnetic field in the region just beyond the heliopause was parallel to the magnetic field inside the heliosphere. The two fields, on opposite sides of the solar system's boundary, were aligned in the same direction. Voyager 2, which crossed the heliopause at a different location in November 2018 and confirmed the result independently, both magnetic fields on both sides pointing the same way. That result challenged theoretical models that had predicted significantly different field orientations across the boundary. The temperature of the heliopause region was the finding that generated the phrase impossible most directly. Inside the heliosphere, the solar wind plasma cools as it expands outward, dropping to temperatures of roughly 30,000 Kelvin in the inner heliosheath. The turbulent region between the termination shock, where the solar wind first slows to subsonic speeds, and the heliopause itself. When Voyager crossed the heliopause, its instruments measured plasma temperatures of 30,000 to 50,000 Kelvin, between 54,000 and 90,000 degrees Fahrenheit. That is between 5 and 8 times hotter than the surface of the Sun. Scientists have nicknamed this region the Wall of Fire, and the name captures the combination of extreme heat and the sharply defined boundary that Voyager's measurements revealed. Heat temperature alone is not what makes it impossible in the scientific sense. What makes it puzzling is the coexistence of those temperatures with stable plasma formation. Normally, plasma at 50,000 Kelvin cannot form or maintain organized structures in the way Voyager's instruments were detecting. The explanation that has emerged from subsequent analysis involves magnetic reconnection, a process where magnetic field lines from the solar wind and the interstellar medium snap together and realign, releasing stored magnetic energy as heat and particle acceleration. The solar and interstellar fields, meeting at the heliopause, are essentially colliding in slow motion across an enormous region, continuously releasing energy that heats the plasma to temperatures that the region's particle density would not allow to reach equilibrium. The heat exists because the density is so low that the particles carrying it rarely collide. Each particle is individually energetic, but there are too few of them per cubic centimeter for that energy to transfer as heat in the conventional sense. Voyager passes through the region unharmed, not because it is shielded from the temperature, but because there are so few particles that even at 50,000 Kelvin, almost none of them hit the spacecraft. Beyond the Wall of Fire, as Voyager continued deeper into interstellar space after 2012, its plasma wave subsystem detected something that scientists described initially as a hum. Not a sound. There is no sound in space, which is a near vacuum. But the plasma wave subsystem measures oscillations in the charged particles surrounding the spacecraft, and what it detected was a continuous, steady plasma wave oscillating at frequencies between 2.6 and 3.0 kilohertz. This hum had been present and detectable since before the 2023 communications crisis, and the analysis published in 2021 by Stella Koch-Ocker and colleagues at Cornell University described it as a faint, continuous plasma wave activity in interstellar space, a gentle drone of electromagnetic oscillations driven by THE density of the interstellar medium pushing back against the edge of the heliosphere. The hum is not powerful or mysterious in itself. It is simply the background acoustic signature of the medium Voyager is traveling through, revealing that interstellar space is not as quiet as previously assumed. Models of the interstellar medium had treated it as relatively quiescent between the disturbances produced by shock waves from stellar activity and coronal mass ejections. Voyager's continuous hum measurement suggests that there's a baseline level of wave activity in the interstellar plasma that does not require an external driving event. The medium is always gently oscillating. On top of that background hum, Voyager detected sharp spikes in plasma density, bursts of electron activity caused by coronal mass ejections from the Sun, whose shock waves take approximately 1 to 3 years to travel from the Sun's surface to Voyager's position at the heliopause and beyond. When these shocks arrive, they cause the surrounding plasma to oscillate more intensely, and the plasma wave subsystem registers them as distinct events above the background hum. Scientists use these events to measure how the plasma density has been changing as Voyager moves deeper into interstellar space, building a continuous record of conditions in an environment no other instrument has ever sampled. Each measurement is a data point from a region of the universe that cannot be studied by any telescope or remote sensing technique. It can only be known by being there. Voyager 1 is there, and has been transmitting from there for 13 years, building a dataset of interstellar conditions that no theoretical model alone could have produced. The 2023 communications crisis and the 2024 recovery are a story that deserves the same attention as the scientific discoveries, because the engineering required to fix Voyager from 24 billion kilometers away is as extraordinary as the physics Voyager is revealing. The fault began on November 14th, 2023, in the Flight Data Subsystem, one of 3 onboard computers built in the early 1970s, whose entire memory amounts to about 69 kilobytes, less than the size of a small photograph on a modern smartphone. The FDS is responsible for taking the readings from all of Voyager's instruments and packaging them into the data format that the radio transmitter can broadcast home. When a single memory chip inside the FDS failed, corrupting approximately 3% of the computer's total memory, that 3% happened to contain a critical section of the operating code itself. FDS could no longer package data. It could only repeat a meaningless fixed pattern endlessly until something was done. Nothing could be done physically. Voyager 1 is at a distance that no rescue mission could reach, and the spacecraft has no capability for autonomous repair. The only path to fixing it was through radio commands. Instructions sent from Earth at the speed of light, taking 22.5 hours to arrive, with any response from the spacecraft taking another 22.5 hours to return. Every single diagnostic step, every test command, every attempted fix required a 45-hour wait between question and answer. The team at JPL that faced this problem had to work from documentation written in the early 1970s, design manuals, circuit diagrams, software listings in Fortran and assembly language, some of it printed on paper in fonts from half a century ago. Many of the engineers who designed the system had retired decades earlier. Some had died. Project scientist Linda Spilker, who had been working on the Voyager mission since 1977, described the diagnostic process as an archaeological dig, sifting through old memos and engineering notes, finding people who remembered working on specific subsystems, reconstructing the logic of decisions made before many of the current team members were born. In March 2024, the team sent a command they nicknamed a poke, an instruction that told the FDS to return a complete readout of its own memory, so engineers could examine its contents for signs of the fault. That readout arrived 22.5 hours after the command was sent, and it was not in the normal readable format. It was a raw memory dump that had to be decoded manually, with engineers essentially reconstructing the meaning of binary strings by comparing them against the original software listings from 1977. When they found the corrupted section and identified the failed chip, the solution they devised was elegant in its simplicity and breathtaking in its execution. The section of code stored on the dead chip could not be replaced, but it could be broken into pieces, redistributed across several different spare memory locations throughout the FDS, and the code rewritten so each piece knew where to find the others. The entire operating code had to be surgically rearranged inside a 1970s computer, remotely, with 45-hour feedback loops, with no margin for error, from a distance of 24 billion kilometers. On April 18, 2024, JPL sent the command containing the relocated code. 22.5 hours later, it arrived at Voyager. The team waited. Another 22.5 hours passed, and on April 20th, 2024, the answer came back. Readable data, engineering telemetry, properly formatted, correctly structured, meaningful. The fix had worked. Over the following weeks, each of the 4 remaining operating science instruments was brought back online one by one. By June 2024, all 4 were transmitting. Voyager 1 was whole again. What came back when Voyager resumed science operations was data confirming what the period before the crisis had hinted, that the interstellar environment Voyager is traveling through is more structured, more active, and more variable than any model built from Earth-based observations had predicted. The plasma density measurements post-recovery showed that the region of interstellar space Voyager is now sampling at approximately 163 astronomical units from the Sun. The farthest any human instrument has ever been, has characteristics that differ from the inner interstellar medium measurements taken closer to the Heliopause. The cosmic ray flux that Voyager detects, the high-energy particles streaming in from the galaxy, continues to increase slightly as it moves farther from the Sun's protective heliosphere. The magnetic field strength, which jumped sharply at the Heliopause crossing, has been holding steady in the interstellar medium with only modest variations, confirming that the interstellar field in this region of the galaxy is organized and relatively uniform rather than turbulent and tangled. And in late 2024, instruments detected what the team described as an anomalous increase in the energy of particles arriving from the direction of the Sun, an event that required the Sun to have released a significant coronal mass ejection more than a year earlier, whose shockwave had just reached Voyager's position and was compressing the surrounding interstellar plasma as it passed. The interstellar medium responded to the shockwave in ways consistent with what theoretical models predict, but the exact characteristics of the compression and the particle acceleration at the shock front provided data points that will refine those models for years. Voyager 1's power supply is declining. The spacecraft runs on 3 radioisotope thermoelectric generators that convert the heat from decaying plutonium-238 into electricity. Each year, as the plutonium decays, the power output decreases by a small but predictable amount. The mission team has been managing this decline for decades, shutting down one instrument or system at a time as power budgets tighten, prioritizing the science instruments that return the most valuable data from Voyager's unique position. By 2025, only 4 of Voyager 1's original 12 instruments remained operational: the plasma wave subsystem, the low-energy charged particle instrument, the cosmic ray subsystem, and the magnetometer. In early 2025, the team made the difficult decision to shut down one of the heaters protecting the cosmic ray subsystem from the extreme cold of interstellar space, in order to preserve enough power to keep the instrument itself running. The instrument survived the cold beyond the temperature range it was designed to operate in, continuing to return data. But the available power margin is shrinking. Projections from the mission team place the point at which the RTGs will no longer be able to power any science instrument at approximately 2025 to 2026. A window that may already have narrowed significantly by the time this is being watched. Every transmission Voyager 1 sends now may be one of the last. The significance of what Voyager 1 has found across 48 years of operation, across 163 astronomical units of travel, across the first direct sampling of interstellar space in the history of humanity, is impossible to overstate. The wall of fire at the Heliopause, burning at temperatures that should not be compatible with stable plasma in a region of near vacuum. The alignment of magnetic fields across the solar system's boundary that challenged models of how the heliosphere interacts with the galactic environment. The continuous plasma hum revealing that interstellar space is never truly quiet. The shock waves from the sun arriving years after they were launched, compressing the interstellar medium in ways that the full dataset of Voyager's instruments is uniquely positioned to characterize. And the 2023 communications crisis and the 2024 recovery, a demonstration that the human capacity for engineering, problem-solving extends to the most distant reaches of the solar system. That 1970s hardware can be reprogrammed remotely across 24 billion kilometers of space with 45-hour feedback loops. That a 46-year-old spacecraft with less memory than a digital photograph can be brought back from the dead by engineers, reading half-century-old documents and talking to retirees who still remember what the code was supposed to do. When the engineers at JPL sent that April 18th command and waited 45 hours for the answer, they were communicating with an object their parents' generation had built, traveling through space their grandparents had never imagined reaching, carrying instruments designed before personal computers existed, returning data from a place that no human instrument had ever sampled before, and may not sample again for generations. Voyager 1 is not just a spacecraft. It is the furthest extension of human curiosity that has ever existed. And what it found when it crossed the Heliopause, a wall of fire burning at 90,000 degrees Fahrenheit in the darkness between the stars, a magnetic field behaving in ways no model predicted, a plasma hum vibrating through empty space, is a reminder that the universe between the stars is not the quiet, cold, featureless void that old textbooks described. It is alive with physics. It is structured and active and full of phenomena that could not be discovered from inside the heliosphere's protection. And the only way to know it is to go there, which humanity did. In 1977, on a spacecraft powered by 2 Christmas tree bulbs, talking home on a 12-watt radio, still transmitting from the dark, from farther away than anything we have ever sent, finding things that should not be possible, and proving, one impossible discovery at a time, that the universe does not care what our models say it should contain. There is one final detail about Voyager 1 that puts everything in perspective. The antenna that sends its signal to Earth, the high gain dish that produces the 12-watt radio beam crossing 24 billion kilometers of interstellar space, must be pointed at Earth with extraordinary precision. The beam is narrow, and the spacecraft is moving, and Earth is moving, and the geometry of that alignment must be maintained continuously across the decades. In 2022, before the 2023 communications crisis, Voyager 1 began sending anomalous attitude data, readings from the system that controls how the spacecraft is oriented, suggesting that it was rotating slightly in ways the team could not initially explain. Engineers eventually traced the issue to a problem in the attitude articulation and control system and rerouted the data through a different computer, resolving the anomaly. But for a period of weeks, there was genuine uncertainty about whether Voyager's antenna might drift off its target and go dark permanently. It did not. It held. The antenna is still pointed at Earth. The signal is still arriving. And as long as it does, Voyager 1 will continue to send back data from a place no other instrument has ever been, proving that sometimes the most impossible thing of all is not what a spacecraft finds in interstellar space, but the simple fact that a machine launched in 1977 with 69 kilobytes of memory is still out there, still working, still talking to us from the dark between the stars.